Hello everyone! Today, we're diving into one of the most perplexing and fascinating objects in our solar system as of 2025, the now famous interstellar comet, 3I Atlas. This comet was officially discovered on July 1st, 2025, and has been a major subject of study ever since. It has astronomers racing to understand it because it's going to be nearly invisible to us for several months very soon. The comet has been showing some unexpected behaviors that have left scientists in awe. And in the past few weeks, particularly in September 2025, there have been new studies and observations that shed more light on its strange nature. We now need to talk about them again because this comet continues to surprise us by changing in ways nobody anticipated. Just to clarify, there's still no evidence of aliens, despite the comet turning green. We'll explain why in just a moment. With data from the James Webb Space Telescope, the Very Large Telescope, and the Gemini South Observatory, we now have a much better understanding of what's happening with this cosmic visitor. However, some of the early assumptions about the comet have changed fundamentally, as it's behaving in ways we don't typically expect from comets in our solar system. It seems to be unusual both physically and chemically, and that's what makes it stand out today. We'll focus on some of the new studies and observations we've gotten so far, all of which are linked below. We'll explore why this comet is so different from the ones we're used to and what possible explanations we have for its unusual characteristics. Let's begin by discussing the coma and the activity of the comet, as that's where most of the mysteries stem from. As a quick reminder, a comet's structure includes a solid, icy core or nucleus surrounded by a fuzzy atmosphere called a coma. This is what makes comets hard to see clearly because their surfaces are often obscured by the coma. For most comets in the solar system, they tend to become visible when they come close to the orbit of Jupiter, about 5 to 6 astronomical units away from the Sun. This is when they typically begin to warm up, and their solid particles sublimating into gas creates the tail we associate with comets. However, the strange thing about 3I Atlas is that it started exhibiting active behavior much earlier than expected. This was confirmed in August 2025 when the Gemini South Telescope showed that it was still growing and releasing more and more material. This suggests that the comet possesses a chemical composition and behavior that is unlike any comet we've studied before. By August 2025, the Gemini South Telescope also captured a significant antisolar tail, meaning it pointed away from the Sun, extending at least 56,000 kilometers, confirming that it displayed classical comet-like behavior. But here's where things take a strange turn. During the early part of August, astronomers noticed that part of the inner coma appeared slightly elongated and pointed towards the Sun. At first, this seemed to indicate another tail, but further analysis revealed that it wasn't a tail at all. Instead, it was a large dust plume being ejected from the sun-facing side of the comet, where intense solar heating caused the icy surface to sublimate more actively. The dramatic heating caused a massive release of dust towards the direction of the Sun rather than away from it. By early September, further observations confirmed that the inner coma had evolved into a fan-like shape. This was an unexpected development, especially considering that comets in our solar system typically evolve much more slowly. The rapid evolution and continuous emission of material gave scientists enough data to start speculating about the comet's core and composition, and based on the latest observations from the James Webb Space Telescope, it became clear that 3I Atlas is chemically quite different from typical solar system comets. Continuing from our discussion, the chemical composition of 3I Atlas has proven to be as peculiar as its behavior. Observations made by the James Webb Space Telescope and the Very Large Telescope have provided insight into what makes this comet so unique. The most striking discovery is that the comet is highly enriched in carbon dioxide, CO. In fact, the ratio of carbon dioxide to water on the surface of the comet is an astounding 7.6 to 1, which is much higher than anything we've observed in any of the comets in our own solar system. This discovery immediately stood out to scientists because, in most comets, the surface is predominantly composed of water ice, with small amounts of other volatiles like carbon monoxide and carbon dioxide mixed in. The high concentration of carbon dioxide on 3I Atlas is significant for several reasons. For one, carbon dioxide has a much lower sublimation temperature than water. This means that it starts to vaporize much earlier as the comet approaches the Sun. The typical comets in our solar system begin to sublimate and become visible when they come closer to the orbit of Jupiter, which is roughly 5 to 6 astronomical units from the Sun. However, 3I Atlas began showing signs of activity from much farther away, much earlier than expected. The high levels of carbon dioxide on the surface helped it to sublimate and become active at a much greater distance than usual, making it visible from a far greater range than any typical comet. This discovery raises interesting questions about the comet's origin. The high levels of carbon dioxide suggest that the comet could have formed in a much colder region of space. Some scientists propose that it could have formed beyond the carbon dioxide ice line, which lies far beyond Neptune in a typical star system. The carbon dioxide ice line is a region in space where temperatures are cold enough for carbon dioxide to condense into solid ice, just as the water ice forms closer to a star. If 3I Atlas did indeed form beyond this line, it would explain the unusual carbon dioxide content, as well as why it has become active from such a great distance away from the Sun. What's even more fascinating is that observations have confirmed that the comet's nucleus is surrounded by a thick insulating crust, which seems to suppress the sublimation of water. This crust likely prevents any water ice beneath the surface from turning into gas and escaping, which further supports the idea that the surface is largely composed of carbon dioxide. Water ice may still exist inside the comet, but the crust is likely keeping it trapped beneath the surface, which is quite unusual compared to typical comets in the solar system. Usually, when comets become active, water sublimates and forms the coma and tail. But this comet's crusty layer prevents that process from occurring, as we expect. This insulating crust could also explain why 3I Atlas has such a bizarre surface structure. The fact that the surface is mostly carbon dioxide with only a small amount of water means that it may not behave like any other comet we've studied. Most comets in the solar system show a strong mix of water, ice, and other volatiles. But 3I Atlas's surface composition suggests that it has a formation history completely different from any comet we know. Furthermore, astronomers observed that the comet was releasing large amounts of material. By August 2025, the Gemini South Telescope recorded the comet's anti-solar tail pointing away from the Sun, extending up to 56,000 kilometers in length. This confirmed that 3I Atlas displayed the classic behavior of a comet, but with a strange twist. As the comet continued to grow and emit more material, scientists realized that the inner coma appeared to be elongated and pointed towards the Sun. This wasn't typical behavior for a comet's tail, which usually points away from the Sun due to the forces exerted by sunlight. Instead, the sunlight side of the comet's coma released large amounts of dust and gas directly toward the Sun, instead of away from it, which further suggested that 3I Atlas had a unique composition and structure that made it behave very differently from comets we've seen before. By early September, further observations confirmed that the inner coma had evolved into a fan shape. This rapid and dramatic change in shape further underscored just how fast 3I Atlas was evolving compared to typical comets. For a comet to change so quickly in such a short time is an extraordinary finding, and this constant activity provided scientists with enough data to begin making some assumptions about its composition and its core. As we continue studying 3I Atlas, one of the most striking aspects of its composition has been the unexpected chemical elements detected around it. Scientists have made some fascinating observations about the materials present on the surface and the gases being emitted by the comet. Early data from the James Webb Space Telescope provided significant clues about the unusual nature of 3I Atlas. The comet's surface shows a striking depletion in carbon chain compounds like C2 and dicarbon. These are molecules typically associated with comets in the solar system, and their absence is highly unusual. The lack of these carbon chains suggests that 3I Atlas follows a very different chemical evolution path compared to other known comets. In solar system comets, these carbon chain compounds are common, and they typically play a significant role in the comet's interactions with sunlight, giving rise to certain colors and emissions. The absence of such compounds on 3I Atlas adds another layer of mystery to its chemical makeup and points to the possibility that it didn't form in the same environment as most comets we study. Adding to the intrigue, the comet has been found to be rich in cyanogen ions, which are atoms of cyanide. Cyanogen is typically seen in cometary atmospheres. But what makes this particular discovery interesting is the presence of an atomic vapor of nickel, which is more commonly associated with certain types of comets. Nickel, like cyanogen, is frequently found in comets, but it is typically accompanied by iron vapor as well. The strange thing about 3I Atlas is the absence of iron vapor. In most comets we observe, iron vapor is usually a significant emission product. But for 3I Atlas, the lack of iron vapor creates an anomaly that scientists are still trying to understand. This further complicates the picture of the comet's formation, as it suggests that 3I Atlas may have undergone a different evolutionary process compared to its solar system counterparts. At the same time, the comet's unusual surface characteristics, being mostly carbon dioxide-based with little water ice, are supported by these chemical findings. The chemical structure and surface composition of 3I Atlas make it clear that it must have formed in an environment very different from the comets that orbit our Sun. The absence of iron and the presence of cyanogen and nickel could mean that 3I Atlas formed in a completely different star system, possibly one that had a unique chemical signature, or where the conditions for the formation of carbon dioxide-rich ice were far more prevalent than in our solar system. The most puzzling aspect of 3I Atlas's chemical makeup is its stark contrast with the comets in the solar system. Most of the comets we observe contain a complex mix of water, ice, and organic compounds. But 3I Atlas's surface is dominated by carbon dioxide. This raises new questions about the environments in which comets form. Could 3I Atlas have originated in a region of its home star system where carbon dioxide ice was more abundant than water ice? And if so, why didn't it exhibit the usual organic compounds we associate with comets in our solar system? These are questions that researchers are still working hard to answer, and they are at the heart of the ongoing investigation into this strange interstellar comet. Additionally, the absence of certain compounds, like C2 or could be a key clue in understanding the comet's formation. While the lack of these compounds is highly unusual for a comet, it suggests that 3I Atlas might have formed in an environment where chemical processes and temperatures were different from those typically found in the outer solar system. This could mean that 3I Atlas was formed in a much colder region of space, possibly further from its parent star, where conditions for carbon dioxide to dominate as the primary volatile were more favorable. Or perhaps it could have formed in a star system with different chemical dynamics, leading to a comet that behaves in ways we've never seen before. What's also unusual is the rapid change in the comet's physical characteristics. As we've already mentioned, the inner coma has evolved from a simple diffuse structure to a more complex fan shape, suggesting that the comet is undergoing rapid changes. This constant evolution, especially considering that most comets in our solar system change much more slowly, adds another layer of intrigue to 3I Atlas's already mysterious nature. Scientists are excited to keep observing this comet to see how it continues to evolve, especially since it's displaying behavior that's unlike anything they've previously documented now. Let's turn our attention to another puzzling characteristic of 3I Atlas that has baffled astronomers: its striking green glow. This unusual color was observed during a lunar eclipse in Namibia by astrophotographers Michael Jagger and Gerald Remen, who captured a stunning image of the comet in the night sky. The bright emerald green color is not completely unprecedented for comets after all. Many comets display a greenish hue. However, the green coloration usually comes from the presence of dicarbon molecules in the comet's coma, which consist of two carbon atoms bonded together, are known to emit a bright green light when they are ionized by solar radiation. This is why comets in our solar system that contain significant amounts of dicarbon often appear green. However, here's the catch: 3I Atlas, as we mentioned earlier, has been found to be remarkably low in dicarbon, which is contrary to what we'd expect from a green comet. This raises a big question. If dicarbon is not present in large quantities, then what is causing 3I Atlas to emit such a bright green glow? This is one of the most mysterious aspects of the comet, and something that scientists are still struggling to explain. The absence of dicarbon and the green glow suggests that there could be other processes at work. Here, processes that are not yet fully understood. The idea that something else is responsible for the green color is still just a hypothesis, but it's an exciting one. Perhaps this could be a chemical reaction that has yet to be observed in any comet we know of. The fact that 3I Atlas is displaying this green hue without the usual chemical signature of dicarbon suggests that we might be looking at a unique form of light emission that has never been seen before. This opens up many new questions about the chemistry of interstellar comets and the processes that take place in the coma of a comet far from our solar system. Adding to the complexity of the comet's behavior is the mystery of its polarization. Polarization refers to the way light waves oscillate. Most natural light sources emit light in all directions, but when light interacts with certain materials, it can become polarized, meaning the light waves vibrate in a single direction. The polarization of light is an important tool in understanding the composition and structure of cosmic objects, like comets. In the case of 3I Atlas, the Nordic Optical Telescope made observations that revealed the comet's coma exhibits an extremely deep and narrow negative polarization branch. This is very strange because negative polarization is not typically seen in comets or asteroids. Even previous interstellar visitors, like the famous Oumuamua, didn't show this type of polarization. This negative polarization suggests that the dust in the coma of 3I Atlas is made up of a unique mixture of icy and dark materials. Makes this even more interesting is that some laboratory experiments have shown that a thin frost layer of water ice on dark surfaces could create polarization measurements, similar to those observed in 3I Atlas. This implies that the dust surrounding the comet is not made up of the typical materials we would expect in a solar system comet. Instead, it could be composed of ice mixed with darker, more unusual substances. This adds another layer of complexity to our understanding of this interstellar comet, further suggesting that 3I Atlas is not like any comet we've ever studied. Some distant objects in our solar system, like Pluto and its moon Charon, have also been observed to exhibit similar polarization effects. These objects, located far beyond Neptune, have unique surface properties that cause similar polarization patterns. So, it's possible that 3I Atlas shares some similarities with these faraway objects, which could suggest that it came from a distant, icy region of space where the conditions for producing this type of polarization are more common. Some scientists have even proposed that 3I Atlas might be related to the mysterious interstellar object Oumuamua. In fact, a recent study on Oumuamua suggested that it could have been a fragment of a Pluto-like object from another star system, based on its unusual shape and composition. If 3I Atlas has similar characteristics to Oumuamua, it might also be a chunk of an ancient icy body, possibly from a distant dwarf planet or another icy object in a far-off region of space. This theory would explain many of the comet's strange features, including its polarization, surface composition, and its very fast, almost undisturbed travel through space. However, we are still left with the question of where exactly 3I Atlas came from and how old it truly is. This is one of the most challenging aspects of studying this comet. As of now, scientists have been unable to determine its precise origin. Recent studies, using data from the Gaia telescope, attempted to reconstruct the comet's trajectory. They found that in the last 4 million years, it did not pass near any major stars, which means it has been traveling through space largely undisturbed for a very long time. Beyond 4 million years, the data becomes less certain. So the true trajectory of 3I Atlas remains unclear. This adds another layer of mystery to 3I Atlas's nature. Some scientists believe the comet could be billions of years older than the solar system, while others think it may be younger, perhaps only 3 billion years old, based on recent studies. The true age and origin of 3I Atlas are still uncertain, but the fact that it is traveling through space in a relatively undisturbed state for such a long period suggests it could be one of the oldest objects ever discovered. As we continue to observe 3I Atlas, there are even more exciting developments on the horizon. One of the most anticipated events that scientists are eagerly awaiting is the comet's upcoming interaction with a powerful solar phenomenon known as a coronal mass ejection, CME. A CME is a burst of solar wind and magnetic fields rising from the solar corona, which is the outer layer of the sun's atmosphere. When these bursts reach a planet, they can create auroras and even disrupt satellite communications. In the case of 3I Atlas, The comet is expected to be struck by one of these energetic bursts in late September 2025. This is a rare and unique opportunity to observe how interstellar ices and dust react when they are subjected to the intense radiation and solar wind from our Sun. The CME is expected to interact with the comet's coma and tail, potentially providing astronomers with new insights into the comet's chemical composition and how its surface responds to solar radiation. This event will be particularly valuable for studying the properties of interstellar materials, as 3I Atlas is the first comet we've encountered that came from outside our solar system. By observing how its surface changes when exposed to the solar wind, scientists can learn more about the physical properties of materials from other star systems and how they behave when interacting with a star's radiation. As the solar wind collides with the dust and ice in 3I Atlas's coma, astronomers hope to see new emissions and changes in the color of the comet, potentially revealing previously hidden components of its chemical makeup. The interaction could also provide new data on how comets from outside the solar system differ from those in our solar system, and it may offer clues about the formation processes of such interstellar objects. These insights will be crucial for understanding the broader picture of how materials in other star systems evolve and how they differ from the chemistry we see in our own solar system. In addition to the expected solar interaction, there's another exciting opportunity on the way for astronomers. In early October 2025, the comet will pass close to Mars, making it visible to several Martian missions. This close encounter will give scientists aboard Mars, orbiters and landers, the chance to capture more data about 3I Atlas. Observations from Mars could provide a different perspective on the comet, and the data collected will add to our growing understanding of this fascinating object. The Martian missions may be able to provide high-resolution images and measurements that will help refine our models of the comet's behavior and chemical composition. Unfortunately, after October 2025, the comet will disappear behind the Sun, and it will be difficult to study for several weeks. This means that for a brief period, we won't be able to track its progress, and scientists will have to wait until it becomes visible again, likely around November or early December 2025. This time behind the Sun will be critical, as the comet could change significantly during its time in the Sun's shadow. The next set of observations will be crucial for understanding how the comet evolves, and whether it survives the harsh conditions it will face as it travels through space once 3I Atlas reappears. Astronomers expect to see changes in its appearance and activity. The data collected during its time behind the Sun will give us valuable information about the comet's structure, composition, and behavior. Scientists will be watching closely to see if the comet survives its journey through this part of space, as comets from outside the solar system are much more difficult to predict than those from our own solar system. The extreme conditions it faces could potentially cause it to break apart, or it could continue to evolve in ways that we haven't yet anticipated as we await further observations. 3I Atlas remains one of the most exciting objects in the sky. Its unique characteristics, including its unusual chemical composition, rapid evolution, and mysterious green glow, have made it a subject of intense study and speculation. The discoveries made so far have opened up new avenues for research, and there's no doubt that more surprises are in store as we continue to track this extraordinary comet's journey. The next few months will be crucial for our understanding of 3I Atlas and its place in the broader context of interstellar objects. As we gather more data, we may uncover even more about its origins, its chemical makeup, and its future, whether it continues its journey through space or whether it eventually disintegrates under the intense pressure of the Sun's radiation. 3I Atlas will undoubtedly continue to be one of the most fascinating objects in astrophysics,